Hello students, in the last class we discussed about kinetic theory of gases. So some of the basic postulates or assumptions what we have considered in kinetic theory of gases, all those things we already discussed in the last class. So one of the most basic assumption what we have considered in kinetic theory of gases is there will be no intermolecular force of attraction between the gas molecules. The intermolecular force of attraction between the gas molecules is absent. So that is the one of the basic assumption we considered in the kinetic theory of gases. So kinetic theory relates the microscopic properties with the macroscopic properties of the gas molecules. So what are the few basic postulates of kinetic theory? So let us just revise all those postulates. So first, every gas consists of what? Extremely small particles which are nothing but molecules. So the molecules of a given mass of a gas are identical but are different from that of the other gas, and the gas molecules are moving randomly in all possible directions with all possible velocities. Their velocities may vary from 0 to infinity. The size of the gas molecule is very less when compared to the size of the gas. Volume occupied by the gas molecule is very less when compared to the volume occupied by the gas, and also the gas molecules, while moving randomly, they undergo continuous collisions with the other gas molecules and also with the walls of the container. So these are the few important basic properties or postulates of what? Kinetic theory of gases. So next, you also discussed about the gas laws. What are gas laws? Gas laws are nothing but the laws which relates the pressure, volume and what? Temperature of the ideal gas. How the pressure, volume and varies with respect to what? Temperature. So that particular variation and those variations are studied through gas laws. These gas laws are applicable only for what? Ideal gases. What are ideal gases? Ideal gases are gases actually which are does not existing in our nature. The gases actually existing in our nature are called as what? Real gases. So first gas law is Boyle's law. Boyle's law gives the relationship between the pressure and the volume. How does the pressure varies with volume? Inversely related. That means pressure of a given mass of a gas is inversely proportional to the volume. So that is the Boyle's law. Next, Charles law. Charles law states that the volume of the given mass of a gas is directly proportional to temperature at constant pressure. When the pressure is kept constant, the volume is directly proportional to the temperature. As the temperature increases, volume also increases. This is about the Charles law. Next, Gay-Lussac's law, third one, which gives the relationship between the pressure and the temperature. At constant volume, when the volume is being kept constant, pressure of the given mass of a gas is inversely directly proportional to the absolute temperature. These are the three gas laws, and you also studied about the ideal gas equation. What is an ideal gas equation? The equation relates the pressure, volume and temperature of an ideal gas. That is PV is equal to RT for 1 mole of a gas, or PV is equal to mu RT, where P is the pressure, V is the volume, R is the universal gas constant, T is the temperature, where mu is the number of moles. So as I said earlier, so whatever the gases present in our nature are not the ideal gases, they are real gases. The gases actually present in our nature are called as real gases. So real gas do not obey the gas laws, and the real gas equation is different from that of what? Ideal gas. Why means while deriving the ideal gas equation, we will not consider the intermolecular force of attraction between the gas molecules, but after considering the intermolecular force of attraction between the gas molecules, there is a correction. Correction is needed for the pressure term as well as what? Volume term. So after making the correction for pressure and volume, we derived Van der Waals derived an equation, real gas equation. That is nothing but Van der Waals equation. That is P plus A by V square into V minus B is equal to RT, where A and B are constants. So this is about the real gas equation. And the next thing is pressure exerted by the ideal gas. So if you take some amount of gas in a vessel, so actually the gas molecules, because of the continuous collisions with the neighboring gas molecules and also with the walls of the container, gases exerts the pressure on any surface which is in contact with it, and hence the pressure exerted by the gas molecules, ideal gas, is given by P is equal to 1 by 3 into capital M divided by capital V is equal to V RMS square, where capital M divided by capital V is nothing but density. Therefore, P is equal to 1 by 3 into rho into Vrms square is the expression for what? Pressure exerted by the ideal gas. The next one is different speeds or various speeds possessed by the gas molecules. Some gas molecules are moving with RMS speed, some are moving with most probable speed, while some others are moving with average speed also. RMS speed is nothing but it is defined as the square root of the mean of the squares of the instantaneous speeds of all the gas molecules. And another type of speed is most probable speed, which is nothing but the speed possessed by the maximum portion of the gas molecules, and the third type of speed is nothing but the average speed. So all these things are actually what we have discussed in the last class, and in the today's class we are going to discuss about the degrees of freedom as well as what specific heats of gases. So what do you mean by degrees of freedom? So as you know that the gas molecules are moving randomly. They are moving in different directions. They are moving in all possible directions with all possible velocities. They are moving randomly because of what? Weak intermolecular force of attraction. Because of weak intermolecular force of attraction, the gas molecules are moving randomly. So in what direction they are moving? So at a particular instant of time, what is the position of a gas molecules in space that can be designated by studying what? Degrees of freedom. So by studying degrees of freedom, you can define or you can designate the position as well as what? The motion of a gas molecule in space. The position and the motion of the gas molecule in space can be given by mentioning degrees of freedom. So when gas molecules are moving, actually they can have three types of motion. So because of their motion, they can have translational motion also, and also they can rotate about their own axis also. They can have rotational motion also, and also they can have vibrational motion also. Whenever a gas molecule is in motion, they can have translational motion, rotational motion, as well as what? Vibrational motion also. And the formula for degrees of freedom. So before going to the formula for degrees of freedom, what is the definition for degree of freedom? So degrees of freedom is nothing but the number of independent coordinates required to specify the position of a gas molecule in space. The number of independent ways in which the motion of a gas molecule can be specified. That is called as degrees of freedom. The minimum number of independent coordinates required to specify the position of a gas molecule in space. That is called as degrees of freedom. For example, if there is only if there is a gas which consists of only single atom, so it can move along x-axis, it can move along y-axis, and it can move along z-axis. Then how many coordinates are required? 3. Therefore, degrees of freedom is also equal to 3. Like that. So by knowing the number of atoms present in a gas, you can calculate the degrees of freedom, or you can find out how many independent coordinates are required to specify the position of a gas molecule in space. So formula to find out the degree of freedom. So degrees of freedom is given by F is equal to 3n minus r, where F is the degree of freedom, where n is the number of atoms present in that particular gas, where r is studied about r, that is nothing but universal gas constant. So its value is same for all the other for any type of gas, that is 8.31 joule per mole Kelvin. So this is the formula to calculate the degree of freedom, that is F is equal to 3n minus r. So here r is not the degree of universal gas constant actually, where r is the number of independent relations. So till now you considered r as universal gas constant, but here number of independent relations or number of independent restrictions. It's not the universal gas constant, it is the number of independent relations. Next, I will consider monoatomic gas. That means gas having a single atom. Example, I will consider helium. Consists of only one atom. Number of atoms is called how much? 1. So number of restrictions. So here there is only one atom in space. It can move along x-axis, it can move along y-axis, it can move along z-axis. It can move along x-axis, y-axis, as well as what? Z-axis also. Therefore, restrictions. So here this atom, there is no restriction for this atom to move along the x-axis, y-axis or z-axis. Therefore, number of restrictions is equal to how much? 0. Then what is the degree of freedom? So F is equal to 3 into number of atom 1 minus number of independent relation or restriction 0. Therefore, degree of freedom is equal to how much? 3. So degree of freedom for monoatomic gas is equal to how much? So by this way you can calculate the degrees of freedom for whether the gas is monoatomic, diatomic or what? Triatomic. So next I will go to the diatomic gas. In case of diatomic, for example, H2 or O2, oxygen gas molecule. How many atoms it can have? It can have only 2 atoms. So how many degrees of freedom? So before going to calculate the degrees of freedom, you have to find out the number of independent relations. So oxygen molecule have 2 atoms. So in between these 2 atoms, this particular distance must remain same or fixed. There will not be any change in this particular distance. Therefore, number of atoms is equal to 2. How many restrictions? So these 2 atoms together can move along x-axis, y-axis as well as what? Z-axis. 3 degrees of freedom required for what? Translational motion. And also, along with this 3 translational motion, this gas can have rotational motion also. For example, if you consider one oxygen atom at this particular end and another gas atom, oxygen atom at this particular end, these 2 atoms can have rotational motion like this. Rotational motion like this or like this also. Like this. So 2 degrees of freedom for required for what? In order to give the designate the rotational motion also. But what about this type of motion? If your gas molecule rotate like this, you cannot observe the rotational motion. So therefore, how many restrictions are there? Only one restriction. So these 2 atoms together can move along x-axis, y-axis as well as z-axis. 3 degrees of freedom for translational motion, and these 2 atoms together can have rotational motion can like this also along the vertical axis or along the horizontal axis they can rotate, but there is a restriction for what? Rotational along this particular axis. Therefore, number of restrictions is equal to how much here? Only 1. So now, what is the formula? F is equal to 3n minus r. 3 into number of atoms 2 minus in number of independent relation 1. 3 into 2, 6 minus 1, that is equal to 5. So degrees of freedom for diatomic gas is equal to how much? 5. So out of these 5 degrees of freedom, 3 degrees of freedom for translational motion and 2 degrees of freedom for what? Rotational motion. So by this way you can calculate the degrees of freedom for what? Diatomic gas. Next, third type of gas, triatomic gas. Triatomic gas means the gas molecules having 3 atoms. So example, H2. H2O, 2 hydrogen molecule, 2 hydrogen atoms and 1 oxygen atom. So actually it is a non-linear type gas. Number of atoms 3. So 2 hydrogen atom, 1 oxygen. So here number of independent relation 3. F is equal to 3 into 3 minus 3, that is equal to 6 degrees of freedom. So I will consider another example for linear, that is CO. So it is an example for linear type of triatomic gas. Here also number of atoms 3. CO2. So in this case, number of restrictions 2 here. Therefore, degrees of freedom 3 into 3 minus 2 is equal to how much? 7 degrees of freedom. So by this way, you can calculate the degrees of freedom for monatomic, diatomic as well as triatomic. By knowing the value of R, number of independent relations, you can calculate the degrees of freedom either for monatomic gas, diatomic gas or what? Triatomic gas. So in case of monatomic gas, there is only one atom. There is only one atom. There is no restriction for this particular atom. This atom can move along any direction. Therefore, restriction is 0. Degrees of freedom is equal to 3. Next, for diatomic, two atoms, only one restriction is there. Therefore, degrees of freedom is equal to how much? Degrees of freedom is equal to 5. 3 for translation, 2 for rotation. Next, triatomic. In case of triatomic gas, there are two types. One is non-linear. For example, H2O. Number of atoms 3. Number of independent relations 3. Degrees of freedom 3. 3 for translation, 3 for rotation. Next, CO2. Here, number of atoms 3. Number of independent relation 2 only. It can rotate along in the vertical axis as well as horizontal axis also. It cannot rotate along its own axis, and hence number of independent relations 2. Therefore, degrees of freedom is equal to how much? 3 into 3 minus 2. That is equal to 7. So by this way, we can calculate the degrees of freedom for monatomic, diatomic as well as triatomic gas. Next, kinetic energy associated with the ideal gas. Any type of ideal gas. So actually, in kinetic gas theory, we will not consider the intermolecular force of attraction, and hence the gas molecules are moving randomly, which means the gas molecules are mainly associated with what type of energy? Kinetic energy only. Therefore, internal energy of an ideal gas is also equal to kinetic energy of ideal gas. Since we are not considering the intermolecular force of attraction, therefore the internal energy associated with the ideal gas is equal to kinetic energy, that is equal to 3 by 2 RT, where here R is the universal gas constant. This is for 1 mole. For 1 mole of an ideal gas, the internal energy, that is nothing but the kinetic energy associated with the gas molecule, is equal to 3 by 2 RT. For mu number of moles, for mu moles, you can write E is equal to 3 by 2 mu RT. For one molecule, E is equal to 3 by 2 kBT, where kB is the Boltzmann constant. Next, for n molecules, if a gas consists of n number of molecules, then E is equal to 3 by 2 n into kBT. So these are the formulas in order to calculate the total energy or the internal energy, which is nothing but the kinetic energy of what? An ideal gas. For 1 mole, mu moles, as well as for 1 molecule, as well as for n molecules. Okay students, next concept, law of equipartition of energy. The name itself indicates law of equipartition of what? Energy. That means energy will be equally distributed. Equally distributed among where? Equally distributed among its all of degree of freedom. Whatever the system is having the energy, the system is having some amount of energy, that energy is equally distributed among all of its degree of freedom. That law is called as law of equipartition of energy. So the total energy of the system is equally distributed among all of its degrees of freedom. That is called as the statement of law of equipartition of energy. So what the energy associated with each degree of freedom is half kBT, where kB is the Boltzmann constant. So for example, if a system is having 3 degrees of freedom, if a gas is having 3 degrees of freedom, so each degree of freedom is going to be having energy is equal to how much? Half kBT. Next, energy associated with each gas molecule. So energy associated with each gas molecule is going to be F by 2 kBT, where F is the degree of freedom. For example, if you consider a monatomic gas, it has 3 degrees of freedom. So therefore, energy associated with monatomic gas is given by 3 by 2 kBT. Next, if a gas is found to be having is a diatomic one, then it is having how many degrees of freedom? 5 degrees of freedom. On that case, energy associated with gas is given by 5 by 2 kBT, like that. By knowing the value of F, we can find out the energy associated with it. And in case if the gas is found to be having n number of molecules, then the formula can be written as for one molecule F by 2 kBT, for n molecule it is F by 2 n into kBT. For 1 mole F by 2 RT, and where for mu number of moles, so energy is given by how much? F by 2 mu into RT, where mu is the number of moles. So this is about law of equipartition of energy. Next, specific heat of gases. You already studied about specific heat in case of solids as well as what? Liquids. So when heat energy is supplied either for the solids or for the liquids or for the gases, so they undergo expansion. When heat energy is removed, they undergo contraction. So when heat is supplied to the gas, there will be increase in what? Pressure as well as what? Volume. If the volume is kept constant, there will be increase in pressure, and if the pressure is kept constant, there will be increase in volume with respect to the increase in temperature. So therefore, gases normally will have two types of specific heat capacity of gases. So gases normally will have two types of specific heats. One is specific heat of gases at constant volume, and another one is specific heat of gases at constant pressure. So how to define specific heat? Remember the definition of specific heat. Specific heat is nothing but the quantity of heat energy supplied to increase the temperature of unit mass of a substance through 1 degree Celsius or 1 Kelvin. So specific heat means the quantity of heat required to rise the temperature of unit mass of a gas through 1 degree Celsius or 1 Kelvin. That is called as specific heat. Specific heat means quantity of heat supplied Q is equal to M into C into delta T, where Q is the quantity of heat supplied, where M is the mass, delta T is the change in temperature. Here this constant is nothing but what? Specific heat. What does it actually indicates? How much heat energy is supplied to a system, that will be indicated by specific heat. So next, specific heat of gas at constant volume. So how to define specific heat of gases at constant volume? It states that at constant volume, the amount of heat energy required to raise the temperature of unit mass of a gas through 1 Kelvin. At constant volume, the amount of heat energy required to raise the temperature of unit mass of a gas through 1 Kelvin or 1 degree Celsius. That is given by the formula Cv is equal to delta Q, heat energy supplied at constant volume, divided by M into delta T. M is the mass, delta T is the change in temperature. This is written by using this relation only, that is Q is equal to M into C into delta T. Just here in the terms, you can easily write Cv is equal to delta Q at constant volume divided by M into delta T. Next, specific heat of gases at constant pressure. How can you define specific heat of gases at constant pressure? Their volume is kept constant, here the pressure is being kept constant. That means at constant pressure, the quantity of heat energy required to rise the temperature of unit mass of a gas through 1 Kelvin. At constant pressure, the quantity of heat energy required to rise the temperature of unit mass of a gas through 1 Kelvin is called as specific heat of gases at constant pressure. And the formula is given by Cp is equal to delta Q at constant pressure divided by M into delta T. Which one is greater, whether Cp or Cv? On which case more heat is required to raise the temperature of unit mass of a gas through 1 Kelvin, whether at constant volume or at constant pressure? So for example, now let us consider a cylinder, a closed cylinder. It is a closed cylinder means here volume is kept constant. Here volume is kept constant. All the supplied heat energy is utilized to increase the temperature only. So since the volume is kept constant, all the supplied heat energy, which is nothing but Cv, is utilized to increase the temperature of the gas only. But in the second case, at constant pressure, in order to keep the pressure constant for the same cylinder, I will attach a movable frictionless piston. Since the pressure has to be remains constant, we have to adjust the volume. Therefore, in order to keep the pressure constant, when the heat energy is supplied, that is nothing but Cp. So piston moves in which direction? Piston moves in upward direction. So here the supplied heat energy is utilized not only for increasing temperature, and also here the piston is moving in the upward direction. That means work is performed. Work has to be done in order to increase the volume. Why volume should be increased? In order to keep the pressure constant. Volume has to be increased. In order to increase the volume, here the piston is moving in the upward direction. So easily you can now analyze the difference between Cp and Cv. Here in case of Cv, all the supplied heat energy is utilized to increase the temperature only. Why means here the volume is being kept constant. Small amount of heat is sufficient to increase the temperature of unit mass of a gas through 1 Kelvin in case of Cv. But in case of Cp, the supplied heat energy is utilized not only for increasing temperature and also to perform the work done. Therefore, which one is greater than which one? So Cp is always greater than Cv, which means more heat is required to increase the temperature of a unit mass of a gas at constant pressure when compared to constant volume. Therefore, specific heat of gases at constant pressure, which is nothing but Cv, is always greater than specific heat of gases at constant volume, which is nothing but Cv. How they are related? Cp and Cv are related by an equation which is called as Mayer's relation or Mayer's equation. Cp is always greater than Cv, which means Cp minus Cv must be a positive quantity. Cp minus Cv is always a positive quantity, that is equal to R, where R is the universal gas constant. That is Cp minus Cv is equal to R is the Mayer's relation. If you know the value of Cp, you can calculate Cv. Or if you know the value of Cv, you can calculate Cp, since R value is already known. It is about law of equipartition of energy as well as specific heat of gases at constant pressure as well as what? Constant volume, and the relationship. That is Mayer's relation. Okay students, last concept, that is representation of specific heat in terms of what? Degrees of freedom. How they are related? Specific heat of gases at constant pressure and constant volume, and the relationship with what? Degrees of freedom. Cv is equal to F by 2R. So if you know the value of F, you can calculate the Cv for any type of gas. For example, monatomic, degrees of freedom 3. Therefore Cv value 3 by 2R. For diatomic, degrees of freedom 5. Cv is equal to 5 by 2R. So like that. So similarly, Cp is equal to F by 2 plus 1 into R. So for monatomic it is how much? F value 3. 3 by 2 plus 1 into R. 3 by 2. How much? 1.5 plus 1. 2.5 into R. Therefore Cp value for that monatomic gas is how much? 2.5 into R. This is the representation of Cv and Cp in terms of degrees of freedom. Next, the ratio of Cp to Cv is always equal to a constant. The ratio of Cp to Cv is always equal to a constant. That constant is nothing but gamma. The ratio of specific heat of gases at constant pressure to the constant volume is always equal to constant. That value is that is indicated by gamma. So by knowing this value, by calculating this value of gamma, you can decide whether the gas is monatomic, diatomic as well as what? Triatomic. For example, if you consider monatomic gas, degree of freedom is equal to how much? Degrees of freedom is equal to 3. Therefore, what is the value of gamma? Gamma is equal to 1 plus 2 by 3. 2 by 3, 0.6. Therefore, gamma value is equal to how much? 1.66 for monatomic gas. While solving any problem, if you get the value of gamma as 1.66, then you can say that type of gas is which one? Monatomic gas. The type of gas is monatomic. Similarly, for diatomic gas, if you consider a diatomic gas, so gamma is equal to 1 plus, here for diatomic degrees of freedom is equal to how much? 5. That is 1 plus 2 by 5, that is equal to 0.4. 1 plus 0.4, that is equal to how much? 1.4. So while solving the problem, if you got the value of gamma as 1.4, then you can directly say the gas is in what? Diatomic gas. Similarly, you can calculate the gamma value for what? Triatomic gas, that is about 1.33 or 1.29, whether the gas is a linear one or what? Non-linear one. This is about the representation of specific heat in terms of degrees of freedom, and also the ratio of specific heat capacity of gases. That is always equal to a constant which is called as gamma. So gamma formula to calculate the value of gamma is 1 plus 2 by F. If you know the value of F, you can calculate the value of gamma for monatomic, diatomic as well as what? Triatomic gases.